Hi, this is Lecture 2 of Unit 2 Basic Chemical Engineering. Unit 2 deals with mass balances in unit operations with non-reacting system and with reacting system. Under the category of mass balances in unit operations with no chemical reaction, the concepts of dry air, crystallization, liquid-liquid extraction, and a mixture is included. I am going to discuss the concept of crystallization and liquid-liquid extraction and the mass balance problems related to these two unit operations. Crystallization is a process of separating solid and liquid solutions. We know that the solution is made up of solutes dissolved in solvent. The crystallization process involves separation of dissolved solute as crystals by altering the solubility of the feed solution. The crystallization process can be carried out by two methods mainly called as evaporative crystallization and cooling crystallization. In the case of evaporative crystallization, heat energy is supplied where some amount of solvent will be evaporating. Because of that, the solution becomes supersaturated, resulting in the formation of solute crystals. In case of cooling crystallization, due to cooling, the solubility of the solute decreases, solution becomes supersaturated, again that results in the formation of solute crystals. Coming to the mass balance of crystallization process, we employ the same methodology what we used in the drying concepts. So the feed mixture is termed as M1, which is entering the crystallizer, and there is only one input in crystallization process. During crystallization, the solvent evaporates. The mass of solvent evaporated is termed as M2, and because of that, the solution becoming supersaturated, resulting in the formation of solute crystals. The mass of solute crystals formed are termed as M4. The remaining feed liquid is called as mother liquor, termed as M3. Each stream will have its own solute percentage and solvent percentage. Here in this slide, I have mentioned as solid percentage and water percentage. Sometimes the solvent will be water because it's an aqueous solution, and the solute will be considered as solid as we were using drying problems. To make the mass balance in crystallization looks like the same what we followed in dry air, I have used the term solid percentage and water percentage. As we did for the dry air, we have to develop three equations. One is overall mass balance equation, that is equating input and output. In crystallizer, the input stream is only one, that would be M1 in this case. There will be three output stream. One is solvent evaporated, the next is the mass of crystal formed, and the third one is the remaining liquid, which we are calling as mother liquor. So the output streams will be M2 plus M3 plus M4. Now next step is to do the solid mass balance. To develop solid mass balance equation, we're going to multiply mass of each streams by its respective solid percentage. So M1 will be multiplied by respective solid percentage. Similarly, we're going to multiply M2, M3, M4 by its respective solid percentage. So that would be the solid balance equation. The next step would be doing the water balance equation, where again the mass of each stream will be multiplied by the respective water percentage. Let's solve a problem to understand furthermore in detail. Let me read the question. A crystallizer is charged with 7500 kg of an aqueous solution of 30% sodium sulfate. So the mass of feed is given and the solid percentage, that is sodium sulfate percentage in the feed solution is given. Let me read the question further. During cooling, 5% of original water is lost by evaporation. So the crystallization process is carried out by cooling here. The line says during cooling 5% of original water is lost by evaporation. Then sodium sulfate dot NH2O is called as Glauber salt. So Glauber salt crystallizes. The mother liquor contains 18% salt. Calculate the weight of the crystals formed, mother liquor and water lost. Generally, while cooling crystallization, the amount of water vapor lost is very minimal. However, for proper understanding of the problem, we are defining the problem like some water is evaporated. The first important point is identify what is the feed mixture data, what is the mother liquor data. Let's fill the given data in the schematic. Some amount of water in the feed is evaporated and we termed as M2. The remaining liquid after the crystal forms, we are calling it as mother liquor, which is M3. And the mass of crystal formed, we are calling it as M4. Let's read the question and fill the given data here. The question says, the crystallizer is charged with 7500 kg of aqueous solution. So, and it has 30% sodium sulfate. So, solid is 30%. Being aqueous solution, the remaining must be water. In similar problem, you can understand that when the solid percentage, that is solute percentage is given, the remaining must be solvent. As the mass is 7,500 kg, I am mentioning M1 as 7,500 kg. Coming to the mother liquor contains 18% salt. The mass of mother liquor is not given in the question, but the solid percentage is 18%, so the remaining must be water, which comes to be 82%. And coming to the water evaporating stream, the mass of water evaporated is not given directly, and we know that the solid percentage in evaporated stream is 0 because the solid cannot be evaporated, and only the solvent will be evaporated. So the water is 100% in the water evaporated stream, solid percentage is 0. Coming to M2, it is given indirectly in the question. During cooling, 5% of original water is lost by evaporation. So M2 can be equated to 5% of water in the feed. The total feed M1 is 7,500 kg. In that, 70% is water. So the water in the feed is equal to 70% of M1. So 70% of 7,500 kg is 0.7 into 7,500. On that, 5% is M2. So the water quantity comes to be 262.5 kg. So M2 value is identified and we can fill in the table. Moving on, we have to find the percentage of solid and water in the crystal formed. The question says Na₂SO₄ 10 times H2O crystallizes. So the moles are given, that is 1 times sodium sulfate and 10 moles of water. We can understand that for every 1 mole of sodium sulfate, 10 moles of water is present. So we need to convert these moles into mass percentage. For that, we are going to use molecular weight. In the question, usually the molecular weight will be given. However, considering this particular basic chemical engineering course, mostly sodium sulfate or magnesium sulfate salts only will be asked for the problem. We are going to discuss 2 problems under this category of crystallization. So the first problem is with sodium sulfate. The next problem will be with magnesium sulfate. So let's convert these moles to mass fraction. By knowing the atomic weight of each element and the respective number of moles, I am calculating the molecular weight of sodium sulfate, which comes to be 142. To calculate the molecular weight, we are multiplying with the respective number of moles into atomic weight of each element. Sodium's atomic weight is 23, sulfur is 32, and oxygen is 16. Coming to water, 10 moles are there, so 10 into hydrogen is 2 times, oxygen is 1 time, so we get 180. Total molecular weight comes to be 322. Total mass of 1 mole of sodium sulfate .10 H2O comes to be 322 kg. Using these individual masses, we can calculate the respective mass percentage. So mass fraction can be calculated by mass by total mass. So sodium sulfate mass divided by the total mass, we will get 142 by 322, which gives us 0.44. Similarly, for water, it is 180 divided by 322, which gives us 0.56. So I can fill the value in this particular table now. We know M1 and we know M2. We don't know 2 unknowns here, M3 and M4. Now we can use the overall mass balance, solid balance, and solvent balance to identify each mass of the streams. In this case, M3 and M4. Overall mass balance equation can be obtained by equating input and output stream. In this case, there is only one input. We are calling it as M1. And there are 3 outputs, M2, M3 and M4. Hence, the equation would be M1 is equal to M2 plus M3 plus M4. Coming to solid balance, we know that we will take the overall mass balance equation and multiply the mass of each stream by its respective solid percentage. Similarly, we do for the water balance equation also. We take the overall mass balance and multiply the mass of each stream by its respective water percentage. Now, let's fill the values for these 3 equations. To start with the overall mass balance equation. In this overall mass balance equation, we know M1 and M2. So hence I replaced M1 and M2 and I have written here. Moving on to the solid balance equation, I know again M1 and M2 and the respective solid percentage. In case of M1 stream, we know the solid percentage is 30%. Hence I have written in fraction, which is 0.3 times M1. Coming to M2 stream, the solid percentage in M2 stream is 0%. Hence 0 into M2 value, that is 262.5 kilogram. Coming to M3 stream, we are multiplying by respective solid percentage, which is 18%. Hence a fraction 0.18 times M3. Similarly for M4. Now we'll do the same for water percentage. We multiply with the mass of the stream with the respective water percentage. In case of M1, the water percentage is 70%. Hence we are multiplying by 0.7. Similarly, we are multiplying for each streams. Let's solve these 3 equations to find the unknown value of M3 and M4. The overall mass balance equation comes to be M3 plus M4 is equal to 7237.5 kg. Solid balance equation comes to be 0.3 times M1 is equal to 0.18 times M3 plus 0.44 times M4. We can simplify this equation by substituting M1 value. So we get the final equation as 0.18 times M3 plus 0.44 times M4. which is equal to 2250 kg. Moving on to water balance equation. Let's substitute the known values like M1 and M2 and find the expression in terms of M3 and M4. So which comes to be 0.82 times M3 plus 0.56 times M4, which equals 4987.5 kg. Let's solve these three final equations to get the unknown value. I have written all the equations here. The first equation is obtained by solving overall mass balance equation. The second equation is obtained by solving the solid balance equation. The third is obtained by solving water balance equation. To solve this equation, we can use calculator. In this lecture purpose, I am solving by mathematical way. So I am going to find M4 in terms of M3. I will get M4 as 7237.5 minus M3. Now the expression for M4 is identified. This I am going to substitute in any one of this equation. This particular M4 expression I am going to substitute in this solid balance equation. Now I am getting an equation in terms of M3. Now rearranging, I can find the M3 and so I can find the value for M4 also.